We are Rover Manipal, an interdisciplinary team of 50 undergraduate students from Manipal Academy of Higher Education, and we are proud to present our rover Vikrant for European Rover Challenge 2026. The team operates across three primary divisions: robotics, research, and management. This framework ensures seamless integration between our technical subsystems and organizational operations. Each division and subsystem are led by their respective heads. The mechanical design and manufacturing subsystem is responsible for designing and fabricating all the rover modules. It utilizes techniques like rapid prototyping, topology optimization, and simulation-based design to develop these modules. The electronics and control subsystem designs and implements the power distribution system and data architecture on the rover. It ensures reliable communication and control across modules. The AI and automation subsystem focuses on rover autonomy, including autonomous navigation, motion planning, and robotic arm automation. The drone subsystem focuses on frame architecture, autonomous control, and sensor integration to ensure efficient, stable, and reliable performance. The life science subsystem analyzes geological samples and environmental parameters using chemical testing and spectrometry to evaluate the potential for habitability. The research division, led by the research head, explores innovative concepts in electronics and AI, participating in publications and conference presentations. The management division, headed by the team manager, coordinates outreach, social media, sponsorship, logistics, and finances.
After our debut year in 2025, participating in ERC 2026 represents a continuation of our commitment to technical excellence and scientific innovation. ERC closely replicates the challenges faced by robotic systems on Mars and the Moon, providing an ideal platform to test, validate, and improve our engineering solutions in realistic mission scenarios. This challenge is an opportunity to push the boundaries of innovation, autonomy, and planetary exploration technologies and represent India on an international stage. Our rover is a standalone mobile platform capable of performing forward and backward motion along with right and left turns. It uses a differential drive system to perform spot turns for these maneuvers and is able to traverse slopes of up to 40 degrees on challenging terrains. The rover includes an accessible emergency stop for immediate shutdown of power. In case of communication loss, the rover ceases operation to prevent damage.
The rover houses a robust electronics and control system architecture built around a modular PCB stack. This modular segmentation simplifies debugging while allowing independent optimization of the power distribution, command processing, and motor control sections. The motherboard regulates system-wide control and facilitates communication between modules along ESP32 and RPI child boards. For safe operation, the microcontroller child boards use onboard current limiting resistors. Integrated status LEDs enable real-time monitoring and diagnostics. The motor driver board is responsible for the actuation and control of the rover's drive systems and submodules. The rover is powered by two 24-volt LiPo batteries managed by the power distribution board. Separate power planes are implemented to protect sensitive electronics from voltage spikes and electrical noise. A custom GUI built using the IMGUI library provides intuitive teleoperation through 8 live camera feeds. The rover achieves reliable communication up to 2 km line of sight and 1 km non-line of sight conditions using Net Metal 5 transceiver, and a backup express LRS link is used for uninterrupted operation. An LED panel indicates rover status: blue for teleoperation, red for autonomous mode, and flashing green upon reaching a waypoint.
New modular space frame chassis has been implemented to improve torsional rigidity and serviceability. Made using 6063 aluminium square tubes to maintain a lightweight structure. It features front and rear sections to mount the robotic manipulator and science module independently. The rover utilizes 10,000 RPM DC motors coupled to planetary gearboxes, having 100:1 reduction ratio to actuate the wheels. A full float bearing assembly has been designed to minimize the load acting on the gearbox's output shaft. We use 3D printed wheels with TPU tires and PLA barrels, balancing optimal compliance and rigidity. The rover's drive system features a patented 5-bar suspension that is kinematically constrained through mechanical stops, along with reconfigurable torsion springs which are used to stabilize the rover over irregular terrain. A 6DOF robotic manipulator is designed based on the 4-bar mechanism, actuated by custom cycloidal gearboxes, achieving a reach of 1.3 meters and the ability to lift up to 7 kgs. The modular end effector features a dual-action parallel gripper using twin lead screw design and is coupled to a bevel differential to achieve pitch and roll. For the surface sampling mission, the science module features a double scoop bucket to collect soil. which is then deposited into the chemical turret. In the deep sampling mission, we use a double gantry system to lower an auger to the surface and collect soil using Archimedes' screw principle. A new 4-wheel independent engine is under development, which is constrained through mechanical stop. A reconfigurable torsion spring along with differential is being used to stabilize the rover. We are also designing a new silicone foam-based wheel with aluminium rims.
For this year's Traverse task, odometry is generated using an extended Kalman filter. It fuses data from the IMU, GPS, LiDAR scans, Z2I point cloud data, and pose estimates obtained from the Uruko tags to improve localization. RTAB map occupancy grids are used to generate the global and local cost maps using data from the Z2I point cloud. Navigation is handled using Nav2, where BT Navigator manages the high-level navigation behavior. NavFN is used as a global planner, and regulated Pure Pursuit is used as the local controller. A custom YOLO V8 model is used to detect Uruko tags up to the range of 20 meters, while OpenCV processes the Z2I camera feed to estimate the pose of each detected marker relative to the rover. A backup GPS-based navigation stack uses haversine distance and bearing for direct waypoint navigation under Nav2 failure.
For the droning subtask, we are using an STM32H7 based flight controller, which is used for position estimation and PID control. The drone features a quad rotor configuration enabling precise thrust vector control through 4 brushless motors driven by a 4-in-1 55 amp ES. It operates on a 4S LiPo battery pack with a capacity of 5000 mAh, managed by a custom power distribution board providing up to 30 minutes of flight time. The drone demonstrates controlled and stable flight with precise maneuverability, executing a sequence that includes vertical ascent and descent, lateral motion to the left and right, and longitudinal forward and backward movement across all axes. Upon completing the maneuver sequence, the drone performs a controlled and accurate landing. An integrated autonomous safety system is also demonstrated separately, wherein the drone initiates a safe auto landing procedure in response to low battery levels or loss of communication signal. The drone is constructed using a carbon fiber frame along with 3D printed components, optimizing for strength, efficiency, and safety. Additionally, we are developing a WhoopX frame variant to further enhance operational safety. For autonomy, MATLAB Simulink is employed to implement an Uruko tag detection, search, and follow algorithm. The drone follows a square spiral search pattern to locate probes and designated landing areas. Communication is facilitated via a 2.4 GHz radio control link using the Radio Master Boxer for low latency manual control, alongside a SIK 100 mW telemetry module for RTK based position and peer-to-peer communication.
Our rover is equipped with multiple tools designed to perform a wide range of tasks efficiently and accurately. A camera is mounted on link 2 of the robotic manipulator to provide visual feedback, while a custom search pattern is used to detect Uruko tags via OpenCV and establish a reference frame for the RM to operate within. Components such as switches, knobs, sockets are detected using custom YOLO models, with OpenCV providing target poses for path planning. Each task is divided into stages: detection, approach, alignment, actuation, and retreat, which are defined using the Move It task constructor. For the science exploration task, the robotic manipulator can also be equipped with a double scoop bucket used to collect soil samples. Our objective is to validate our falsifiable hypothesis through visual reconnaissance and qualitative analysis. This is achieved through multiple chemical tests designed to detect proteins, carbonates, labile carbon, and the pH of the soil. To aid in live determination, a custom-built fluorometer is used to detect DNA and RNA. The deep sampling model includes a 30 cm sheeted auger, which is lowered by 2 lead screw-driven gantries. The sheath guides the soil upward to a separate cache on the auger for storing the sample. For surface and subsurface sampling tasks, weight sensors are incorporated into cache containers to measure the mass of collected regolith and rock samples. The liquid sampling system is designed as a swappable end effector, combining a peristatic pump guide mechanism with a pH probe.
For regional geology analysis, we've selected a site within the impact basin of Hellas-Phoenicia, revealing the complex geological history of Mars and how various fluvial and volcanic processes have shaped its surface. From billions of years ago, this area features valley fills, debris aprons, and collapse pits. Remote sensing tools like JMARS, HiRISE, and CRISM provide insights into surface composition and morphology. We are also developing a custom Raman spectrometer for on-site missions, enabling detailed qualitative and quantitative analysis of minerals present in the soil.
We are excited to return to the European Rover Challenge for our second on-site participation. Building on our experience from ERC 2025, we look forward to showcasing our latest innovations and competing with teams from across the globe. See you at ERC 2026.